Right, you remember that Pascal's triangle thing, or you just write this 3 times and multiply, 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 right? And anything without an h in it should cancel. So if you have something with no h in it that doesn't cancel in that first step, you're doing something wrong. Why is that? What do I want to have happen now, of course? What's the fundamental problem with this guy? Yes, and so it's 0 on the top and 0 on the bottom. So you hope that the reason it's 0 cancels. So really that boils down to an h has got to cancel. Which is why all this shit without an h should go away. So that could happen. So now everybody loses an h. So then I end up with 3x squared plus 3xh plus h squared. And of course that just becomes 3x squared, because everything with an h goes to 0. And of course that is what we know the derivative of this is supposed to be. I like it. It's good to do this every now and again, so you know that everything we do is based on this, which is based on algebra, which is pretty concrete. Maybe. Okay, so that's number 6. Number 7 is my attempt to make sure you know how to graph things on the graphing calculator. This is just like when I gave you like this kind of picture and you had to draw the derivative on top of it. Except now I'm saying give yourself the picture on your calculator and then graph that. So if you haven't tried this yet, I didn't bring graphing calculators, but hopefully you have one. I guess I ain't going to move to the projector. Not a projector person. Oh, I guess I don't need that. I can use this. This one. This one. Are you zoomed in? No. Okay. All right, let's take a look here. It's a cool sound. There we go. And random projector over here. Okay. So I've got. Holy shit, that's bright. No autofocus stop. So this dude here. Y equals x cubed minus 3x squared. I want to graph that bad boy. I'm going to do zoom 6 just to make it a standard window. Sweet. And some of this we should know already. I mean, on one level you should, well, hello. Be able to look at this and tell right away what the intercepts are, what the x-intercepts are. see them on the screen now, but 0 and 3, right? So that makes sense there, thank God. That's your standard kind of f of x that they give you, that you have to do f prime on top. I pretty much do that without even thinking, a little cubic figure. So how would you graph the derivative of this? Can you take a minute and try to graph the derivative of this? Try to capture this like it's dotted on your picture. Draw a rough sketch of this. It doesn't have to be perfect. You can see where it goes through. You can see about how deep that is. Fill it in. And then on top of that, plot the f prime. Full battery. Wow. Yeah, kind of crappy, aren't you? Let's do over here. Okay, so let's see. It's a paper. So to capture this, I've got going through there. 1, 2, 3. It's about 1, 2, 3, about 4 deep here. Bop. You said dotted line, Jeff. Oh well. Too bad, I forgot. Now, on top of this, yeah. See, it looks exactly the same. It's amazing. It's like looking into a mirror. So now, what's happening back here? Where am I going to start to do my f prime? What's happening back here? Huh? Positive slope. Big positive becoming smaller. You guys with me? It's big positive, and then it's approaching, of course, what here? So it is 0 right there. That's kind of a coincidence that it's lining up with the actual physical point. You with me? But there's a 0 slope here. Where else is there a 0 slope? Looks to be about 2, right? You guys with me? Yes? Sure. And of course, it's big positive becoming smaller. And of course, in here, what's true? Besides, it's really shitty graph. I love it, Jeff. Let me just overstate this a bit. There we go. And there, what's happening? The slope is negative, getting bigger negative until about right there. What was the name of that point where the slope is the biggest? Yeah, the inflection point. I love it. So it's big negative, and then about right there it should hit its little vertex, right about where the slope is the biggest negative, and that should make sense. That's where the slope should dip the most, is where it's most negative, and then it becomes less negative. And of course, after this, it becomes bigger and bigger positive. And so it does exactly what we expect it to do. It started off as x cubed. The derivative should look like an x squared. You guys with me? And of course, we can now check this. What is the derivative of this? 3x squared minus 6x. It's in red too. I like that. I didn't plan that. Woohoo! Which is, look at that. Again, looking into a mirror. It's amazing. You guys with me? A little bit? All right, maybe. Okay, hopefully that's clicked, because it's one of those things that just has to click. about how to look at a graph and start to graph its slope. The first few times you do it, you're like, where am I supposed to be? But you really are graphing the dots related to what the slope is at those points. That's what you're doing. Okay, maybe. And you got great ways to check yourself now. If I give you the function, you can check yourself. Check yourself. Okay. There. Oh. What intervals is it increasing, decreasing? The original function. Let me take away the slope function. Get away. Look at the original function. Where is it increasing? What interval? Say again? Good. Negative infinity to 0. Do I include 0? This is an interesting question. I think the book does, and they are stupid. What's happening at 0? Is it going up, going down? It's flat at 0. So, of course, I'm not going to include turning points or even resting points in my answer for increasing, decreasing, because it's not doing either one at that point. I love it. So, like if I throw the pen up in the air at its apex, it's not going up or down. It's just sitting there for a second like, oh, shit. And then it starts falling. Where else? Is it decreasing or increasing somewhere else? Yeah. About, looks to be 2. How can I make sure here on the graph? How can I make sure that it's 2? I can calculate the minimum. Weehaw! Enter the left bound, enter the right bound, enter my guess. And it looks like it's trying to tell me 2. This is the calculator saying, I can't quite get this. It's 2. So 2 to infinity. And of course, where's it decreasing? It must be what I left out here. Yeah, 0 to 2. You gotta love that shit. How we doing? Yes, no, maybe? Here's a nifty question. All right. How do I find the inflection point exactly? So f of x was x cubed minus 3x squared. F prime was 3x squared minus 6x. How do I find that inflection point? So the inflection point on the original graph was the point where the slope is biggest, negative or positive, in this case negative. What does that relate to on the graph of f prime? What's happening at f prime? Vertex, which is where the slope is 0. So f, I really want you guys to get this. F prime is a function in its own right. Any function I've ever seen could itself have been an f prime. I could figure out where it would have come from. What would I take the derivative of to get to this function? So just because I took the derivative of a function to get to f prime doesn't make it any less of its own function, right? Like your mom had you, you're your own person, right? That's a little far, Jeff, but I don't care. You guys kind of with me? All right, maybe. Some of you maybe more than others. So how do I find that inflection point translates to how do I find the horizontal tangent line point of the f prime, which means I have to take another derivative. How do I find the minimum of f prime? I take its derivative and set it equal to 0. You guys kind of with me? So you don't even have to necessarily think of it as taking a second derivative. I have a function, f prime. How do I find its minimum? Take its derivative, set it equal to 0. So let's double check and make sure maybe this is, what did I get, 2? What's the second derivative of this? 6x minus 6. So it should really be 1. Yeah, so my graph just looks crappy. Okay, maybe. That's a little extra step there, but it just, since I brought up inflection point, so the inflection point of a function seems to relate to its second derivative. So that's going to come into play later this semester. Okay, I don't want to push that too much. Now, so we did 6 and 7. They're not on the answer key. We did them together. We could do anything else. We could do quiz questions. We could do homework questions, practice test questions. Why the shit does something work questions is anything. But no questions means we're going to sit here and look at each other for a little while until I get bored and we leave. Yes?
We do a few questions from 3.9, but just practice.
Sure. What'd you have back there?
Number 6, how did you set up the equation again? The one that you just did on the board.
Oh, this.
Yeah.
Oh, how did it get here?
Yeah.
You just do x plus h cubed. So either you remember that Pascal's triangle shortcut I showed, or you just write x plus h, x plus h, x plus h, foil, foil.
Okay.
Right, you got to cube this. The big mistake that I still see some people doing is they'll say, okay, f of x is this, so f of x plus h is this, of course, yay. Yay, that's bullshit, right? That's utter bullshit. That should not be happening at this level. I got to plug this in here, which means I got to cube x plus h. Then you write this thrice. Ooh, thrice, Jeff. Yeah, I like it. You write that 3 times, multiply, 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 so you go crazy. Or you know Pascal's triangle, and you go right in there quickly. You know it. Is that cool? Is that right? So I'm not going to give you like a 5th power and say, use the definition, limit definition. You know, that would just be me saying, yeah, I'm going to give you some busy work. Right? Maybe a cube would be the most I would do. But you know I might give you a square root. I might give you 1 over x squared. You know, something more interesting than 3x minus 7. It's not very interesting. And you're like, I'm okay with boring, Jeff. Oh, that's too bad. Okay, so let's see, 3, 9. That's really, I mean, that is the best question. Is everybody aware exactly which sections are going to be on the test? 2, 8 through 3, 9, not including 3, 7. We're going to do 3, 7 for the next test. 3, 9 is the related rates section. So I did give a few of them on the practice test in the little list of problems from the book. But we could do, if there's a specific one that's troubling you, we could do that one, or I could just randomly pick one from the section. We can have people call in and give suggestions. Yes?
I don't know what number it is in the book, but it's about the brain weight
Ooh,
as a function of the body weight.
I like it. So tell me, what's that look like? It might be in here somewhere, but I'm not going to. There it is. I see it. Has been modeled by the power function. Mine says 0.007 w to the 2/3.
Yeah.
Yeah? Okay. So they give me brain weight as a function of body weight in fish. All right, so don't start doing this and figure out how heavy your brain is. 3 grams? What? 0.007. Wow, you'd be a pretty damn big fish. W to the 2/3. So whatever the weight of the fish is, I can take the 2/3 power of it, multiply with this, and that gives me an estimate of the brain weight. I like it. So we're assuming this equation is true, although it's probably an approximation. B and W are measured in grams. A model for body weight as a function of body length. Ooh, I like it. So now we get a next level. Body weight as a function of length. Oh, let me see if I can see this correctly. I got one functioning eyeball. Mine says 0.12 L.
2.53.
2.53, yeah. Did I ever tell you guys about that? That I got like 50% vision in this eye. Like January 3rd, I lost all vision inside. That was exciting, just out of nowhere. Right? And come to find out, it was like a genetic predisposition. So now I got to get, I'm not going to go tube, I got to get shots in my eyeball. Yay! But now I can actually walk around like this, whereas before I would have not been able to. This would have been bad. Right? If this eye goes, though, I'm done. Oh well. That's a little freaky. So just in case I'm like, I tell my students this sometimes because you'll hand stuff to me and I'll be like, where? Or you can sneak up from this direction. You can go, whoa. There, all right. So this one says, if over 10 million years, the average length of a certain species of fish went from 15 to 20 centimeters, over, what was it, 10 billion years? Yeah. At a constant rate, how fast was the species brain growing when the average length was 18 centimeters? All right, now this is a really interesting way to give you a piece of information. This is direct. They're asking me, what's in symbols? What is it they're asking me? According to the formulas I've got, what is it they're asking me in symbols? Shit. Where are you? Yeah, so in symbols, what would that be? That's still English. I want mathish. Good. DBDD. DBDD. DBDT. So they're asking me what DBDT is. What is this telling me? This is how much what changed over what? Yeah, so this is DLDT. Can you tell me what that is? I mean, all you got to do, this gets really interesting. It's going to be very small. Because how much did it change by? The length changed by? Okay, so it's 5 centimeters per 10 million years. So it's half a centimeter per million years. Okay. Let me stop. So every million years they get a half a centimeter longer. That's nifty. Sort of like humans. We used to be pretty damn short. Of course, compared to me, it wasn't that much of a difference, but still. And then over time, we got taller, and now we probably shrink it again because of all the bad economic times. Too bad for us. You guys, everybody with me here? So this is a very different way to give us this. They normally just tell us this. And this problem's like, I ain't doing that work for you. Here's the shit. You make the ratio yourself. But it's just algebra. 5 centimeters per 10 million years. That's DLDT. All right, now, how do I do this? I have information about the length, and they're asking me a question about the brain. And that's why they had to give me both things. Now, to be honest, there's a very direct way you could do this. And then there's a way you could do this 2 steps. I love you guys so much. Is there a function of brain weight, a function of length? Could I create that? Could I have brain weight as a function of length? Totally. What do I do? I know what W is. So I put all this shit there. Now, if you don't feel that that doesn't really appeal to you, which part of me doesn't blame you, doing it the other way is just as much, or the same amount of work, to be honest. So the other way would be, now please, dear God, I mean, whenever I'm doing a problem like this, you have to focus on what is it that's driving him to do the next thing he does. The actual individual things I'm doing and what they are, no, it doesn't matter. What matters, because I'm not going to give you this problem. You're not going to get a fish weight brain length problem. You're not. You're going to get a problem just like this, right? Involving the same steps. So you got to pay attention to what's making me do the next thing. So I know they're asking me this question, so let me figure out what DBDT is in general. What is DBDT? What happened back there? Somebody leave? Oh, somebody left. Okay. We could do this. What's DBDT? Here's B. So what's DBDT? What's going to happen here? 2/3 comes down. Don't freak out. So it'll be 2/3 of 0.007. And what happens to this piece? It becomes W to the negative 1/3. Somebody's whispering it. I always like that. Times, what am I taking the derivative with respect to? What am I taking the derivative with respect to? Time. If I was doing it with respect to w, wait, I would be done. Why am I not done? Huh? No. I'm doing it with respect to time. So what am I missing here? dw dt. I like it. I like it. What drove me to do that differentiation? Because that's what they're asking me for. So of course I'm going to create the dB dt function. Now, does it involve what they tell me, though? Does that equation involve this? No, shit. So that's why I've got to do this. And that, now you maybe see the link. So if I do dw dt, what do I get? I'm not asking you to do the multiplication. Just tell me what it would become. 2.53 times point, get out of there, 0.12 L to the, 1.53, that's neat, times dl dt. I like it. Now, if you are right now not sure why that's there or why that's there, that is the main point of this section, which I'm not saying to make you feel bad. I'm saying to make you realize, figure it out right now. Be sure to know when to do this. There's one problem in the homework I love. Is it gives you a volume formula. It says take the derivative with respect to radius. Take the derivative with respect to height. Right? I love that problem. Because it's really focusing you on this is what's the most important thing. I didn't do it with respect to W. I did it with respect to T, so that's got to be there. W's got to get a chance. I really want you to get this. If I had B equal 007 W 2/3, what would dB/dW be? 2/3, 0.007, W to the negative 1/3. Now watch, I'm going to do an extra step that we don't have to. I'm done. But then it would be times dW/dW, and which is 1. So of course it wouldn't show up with respect to itself. But this is with respect to time. That's got to show up, because that's not 1. I don't know what the shit that is. Can I figure out what that is? Yeah, because I know what that is. Right? I know what that is. There. And length is 18. So I can figure out what dWt is and plug it in there. Okay, maybe. Is that all right? Who asked that question? Oh, yeah. Shan. Is that all right? Are you with me so far?
Yeah, I did it that way, but I still got the wrong answer.
So then, let's see. So I can figure out what dW dt is because I know what L is. So I plug a 30 in here, and I get what dW dt is. I'm going to get what that is. They're asking me for this. I'm going to know what this is, so I can just plug it in. What is it that I don't know still here? They asked me for this, so it's fine. I don't know that. I know this. I will once I do this step, right? So what's the last thing I don't know? W. Can you figure out what W is? Well, shit, yeah. I know what L is, so I can figure out what W is, right? So when you get into this kind of problem, sometimes students forget that you have these. You know L. I know L. It's 18. At a point when L is 18. And this one says, I need W. Oh, shit. Oh, I know L, so I know W. I have a relationship. This is all about relationships, related rates, but this is related variables. That's what an equation really is a relationship between unknowns. Oh, man. Students normally hate that kind of problem because it's multi-step. But, oh well, that's real life. So here, I would plug a 30 in and get whatever the hell that is. And I know this is, where'd it go? 1/2. So what are my units in? Yeah, I'm sorry, 18. I don't know where I got 30 from. What are my units going to be? We already set it up. Centimeters per million years, right? Yes? I mean, I can look right there and see what my units are going to be. Centimeters per million years. All right. Once you know this, you just plug stuff in there, figure out what this is, plug it in there, figure out what W is, put an 18 here, figure out what W is. It's a bunch of substitution now. Yeah?
So when you do line it all out, you plug in all the numbers, you get this big long equation, you do the math, and you get an answer. It's either a decimal point or something like that. But the answer online required like a 10 to the negative 8. Do you still get that when you multiply?
Oh,
everything
no,
out?
online they might have been more specific and said per year.
It was the exact same question.
But I didn't read the whole
Anyways,
thing.
I'm just.
It might have
Is there any
said,
way that you would get that doing it this way?
of course.
Because that's the part I didn't get.
What is a
I got an
million? What is a
answer, but-
million?
Well, no, it's 10 to the 7. I know that.
Okay.
But when you multiply all of those numbers out, like you're just saying, plug everything in and you get this big long equation, you get like a decimal point answer.
Sure.
You don't necessarily get like an E or like a 10 to the.
Well, of course not,
You know what I
because
mean?
what is buried in here is it's times 10 to the negative 7.
Right,
If I brought this up, right?
right.
I like it. And 1/2 times 10 to the negative 7 is 5 times 10 to the negative 8. 0.5 10 to the negative 7 is 5 times 10 to the negative 8. There's where your 10 to the negative 8 comes from. So there might have been, this one is not that specific, but it might have said per year, which means, and sometimes when they give you the little box online, they put the units next to it. So if it's per year, oh shit, then you got to bring this million in and actually write it like it is. Yeah. Here, my answer is going to be per million years, which is fine. But they might have been more specific. They want it per year. Oh shit. Okay, I like it. Yes.
You mentioned that the units are centimeter per million years. Why
Yes.
isn't it grams? Because
Well, I mean, once you do this work, this is going to be, so this is centimeters per million years, right? What they're not telling you is this has units. Think about this. So this must have units, but they didn't tell it to me. This little constant here, because weight can't equal length to this. You with me? So what's this going to be? This is going to be grams per million years. I like it. And this will be grams per million years. Okay. All right. So there is a bit of a hidden thing here with the units on this. But you know what the units should be. Once you write dW dt, you know what the units are. Well, the unit's going to be grams per million years.
yeah, but that was my question because you put it originally at centimeter per million.
Yeah, this is centimeters per million years. Yeah. Yeah, I like it. So really what that's setting up is it's per million years. So if you're at all curious, what's got to be the units on this guy? Really, right here I can tell what the units on this guy is. This is centimeters, and this is grams. So this must be 0.12 grams per centimeter, so that the units match up. You guys love this problem, I know. Does not get weighted down by the units necessarily. That's a part of this problem, but you understand the process to go through. There was a problem on the practice test that dealt with volume and surface area. It's basically the exact same idea, just a little bit neater. There's no 2.53 or per 10 million years. But it's the same idea. It's two separate. There's volume and surface area, just like there's this and this. And you have to do very similar things. to get to the answer. Okay. Where do you guys want to go next? Is that decent for that? So I think on the practice test, shoot, I gave all of them away. Number 97. 97 under number 5. I think number 5 is the one that's got all the problems from the book. So number 97 in that list. That's just like this, but it deals with volume and surface area of a cube. It's a lot cleaner of a problem. Okay. Can you guys see what's making this problem muddier is per 10 million years. These disgusting numbers, they all kind of go on top of what's really important, which is the calculus steps we take. Okay, where else do we want to go next? Could be a homework problem, could be a practice test problem. Could be just a general, why does something work problem.
It's a general concept, not sure if it's related to the test. You mentioned the last lecture that the first derivative is velocity, the second is acceleration, the third one is the jerk.
Oh, if I'm given a position function, the first derivative we call it velocity, the second derivative we call it acceleration, and the third derivative is the one that's not used as often, but it's called the jerk. And like I said, when I first heard that, it made total sense because one of my first cars was all about that. Step on that gas pedal, maybe yes, maybe yes. So that would be the change in acceleration, right? But that's going to be from that section we skipped 3.7.
Okay.
Yeah. So there are situations where certain functions, their derivatives and their further derivatives, we actually give names to. And that's the most common one right there. Position, velocity, acceleration, and then of course, jerk is not very common, but I like it. So be very nerdy and call somebody a third derivative. It's not only is it nerdy, it's not very funny, but oh well. Yes?
Do we do another 3-9 problem?
Mm-hmm.
Just for everyone.
Anyone?
Yeah.
All right. Oh, cool. Oh, shit. All right. Let's see. No, all right. Let's do one. Let's do a couple. Let's do a classic one. It's number 33. Whoa. Okay, that's a little freaky. There we go, Jeff. The top of a ladder. Yeah. I don't know. This might be one I assigned. I can't remember. Top of a ladder slides down a vertical wall. Where'd it go? At a rate of 0.15 meters per second at the moment when the bottom of the ladder, blah, 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 blah. All right. So what do you have to identify with variables here? Do I care about the angle? Do I care about the angle? What is it that tells me I don't give a shit about the angle? There's nothing in there about radian. There's nothing. So why would I even introduce that idea? So this is not going to be necessarily a trig idea, but let's see what happens. What do I have to identify, though? It slides down a vertical wall at a rate of 0.15 meters per second. So where is that on this picture? In this triangle, what is it related to? Sliding. The y. I like it. So let's call this y. Is that cool? So what's dy dt?
0.15 meters.
Yeah, 0.15. I like it. And then let's see what else we need. At the moment when the bottom of the ladder is 3 meters from the wall, so what else gets a variable name? Why am I not just going to put a 3 here? Because what's happening as this thing slides down, it must be shooting out, right? This must be changing. So the snapshot numbers don't come in early. They come in after I've done derivatives, or else everything just becomes 0. You plug a number in, you get a constant, derivative 0, you're like, these are all easy, Jeff, they're all 0. So this one I'm going to call, amazingly enough, I'm going to call it x. What else do I need? Because what are they asking me for? Well, I'm sorry. Right now, what can I put down? dx dt. Yeah, 3 meters is the length I want x to be. That's the snapshot I'm going to take. So I really want you guys to see, I set up the general situation with variables. Then, after I take derivatives, I can plug in the snapshot numbers. So that 3 meters is going to be the snapshot. So I know eventually I'm going to say, at a point when x equals 3, I want to figure some stuff out. So dx dt is 0.2 meters per second. It slides away from the wall at a rate of, okay, that's how much this is changing. So this step is crucial. I haven't done any calculus work at all yet, and that's beautiful. Your first steps and your last steps are often not calculus. Just the middle couple steps is calculus. Right now I'm just capturing what the shit they're talking about. Let me see, blah, 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 blah. And how long is the ladder? So obviously I want this, and remarkably enough, I'm going to call it L for, length of the ladder. You can call it whatever the hell you want to, right? I like it. So what relationship am I going to use? It doesn't look like it. My poor building looks like it's gone through some shit, but that's a right angle, right? So what relationship I'm going to use that relates all the variables. So I want to write an equation that relates all the variables, because then when I take a derivative, I get an equation that relates all the rates. The title of the section is awesome. Related rates. If I have an equation relating variables, derivative makes the rates related. It's awesome. That's a crazy, beautiful idea, to be honest. Maybe just to me, but. So what equation am I going to use? Yes. Old Greek dude that stole all that shit from his followers. Right? And then, of course, what do? Now watch this. What am I going to get for the derivative of this? 2L. Now what would you think goes here? And you're not wrong if you put this, but what is dl dt? What is L? The ladder length, right? So it doesn't change. So really, this is all 0. What's the derivative of L squared? 0, because L is a constant. Thank God, we could have made this problem so disgusting if I would have allowed the ladder to one of those ladders that kind of the middle part goes up. So it could have been changing the length. Oh, God. No, you don't want that. But here, it's obvious from the question, the ladder is a fixed length ladder, thank God. Right? That's a real easy thing to miss in this problem, because you guys get derivative happy. We know this. You got to identify your constants and let the derivatives be easy. This side's derivative is 0. Then what are you here? dx dt, I like it, plus, where's my, oh, there's 2y, dy dt. What do I know? Do I know dx dt? Yes, do I know dy dt? Do I know x? Yes, do I know y? Shit, see now I bring in snapshot. Now I want to plug stuff in. At a time when these things are true, what's the rate? And actually, it's asked me what L is. I'm going to have to work backwards to figure out what that is. Oh, okay. I'm being silly. So how in the world do I figure out what y is? So what do I know is true at the snapshot? Now that I've taken the derivative, now I bring in the snapshot. So at the snapshot, what is this? 3. Do I have another color? Yeah, you do, Jeff. So this is 3. Oh my God, poor little dude. This is still L. So can I figure out what this is? Now this is, I love this problem. I like it even more than I thought I would. You would, Jeff. Now, I really, again, what's my motivation here? I wrote down everything they told me with symbols. I drew a picture, actually, before I did that, to be honest, with everything identified with variables that will change. Right? Now, this L is constant. There's a problem. But these two needed variables because they could change. It's sliding down, it's sliding over, and I have those rates of change. I love it. Then I took a derivative. And now I know this, I know this, I know this. Oh shit, I got to figure out what this is when x is 3. So what is this equal to when x is 3? What do I have to use again? Pythagorean theorem, I love it. So y would equal, I don't know, guys, whenever you know the hypotenuse, it's going to be square root of L squared minus, in this case, 3 squared. So square root of L squared minus 9. So now I can plug that in. I love you guys. And why does that help? It's kind of funny. I realized that a second ago, and then I just got anxious because I didn't see something in here. What is this question asking me about? The length. Do you see L in here anywhere? That should kind of trouble you. But when you go through and say, what do I know? I know this, this, this. I don't know what this is. You can write it in terms of L now. So now I can solve for L. I can plug in this, I can plug in this, I can plug in this, plug that expression in, solve for L. I like that problem. Yes?
Couldn't we have also solved for y and then made it equal?
Totally. And then, yeah, you could do this. You could solve for y, put it back in, and then figure out what L is. Kick ass. Right? That might even look better. So, all right. It always sucks. I'm sure you've had this experience where a teacher's working at a problem and then they get lost. You with me? Have you ever experienced that? And as a student, that's frustrating. But personally, I like that experience because you need to see what goes into solving a problem. When I look at a problem, I don't know exactly how it's going to shake out. I have no idea what all the steps are going to be. But I know how to start attacking it, right? So right here, this wasn't an example where I messed up or something, which that could totally happen. But I actually like your method better, right? I'm like, okay, yeah, we could solve for y, plug it in, figure out what L is. That would make it look prettier, right here, right? I love it. So let's see. Let's plug in everything. Can the 2's die? Yes. So we got 0 equals 3 times dx dt was 0.2 plus y times 0.15. Oh, and I did leave out something, didn't I? Yeah, here's one little thing I left. Let me see if you guys are cool with this. I got to be more careful myself. What's really true about this is the length, is y growing or shrinking? Shrinking. So what should this really be? Negative. Over time, is y getting bigger or smaller? Well, the ladder's going down, so y is getting smaller. So this 0.15 should really be minus. What kind of told me right there I had made a mistake was I was going to get a negative length for y. Well, that's no good, right? But that's a part of the process. It doesn't mean you suck. It just means, oh, I forgot. You go back and see what physically makes sense. Oh, this is shrinking. It should be a negative change. Now it's going to actually make sense. So now I can solve for y. Right? This will be 0.6 divided by 0.15. which is a nice 4. That kicks a lot of ass. So then what's the length? 3, 4, 5. 5. We can do it. 5 meters. Kick ass. Ooh, that was a yummy problem. This is the kind of problem you guys hate, and it's I feel like it's because you haven't got enough practice seeing what leads you to the next step. Right? When you guys watch me do a problem, this is why I don't want to be too polished with any problem, because I want you to see what I'm thinking about as I'm setting a problem up. If I come up with a problem already done, you're not going to see that shit. Now, of course, that also leads to me making mistakes sometimes, but, I accept that. I'm fine with that, because that's what we do. Maybe. We can let's do one more, a different type. All right, if this eye is going to be all blurry, I'm going to be in trouble. There's the trough problem. I like it. Ooh. Well, you get a problem like this. Oh, shit. Look at 24. That's a very direct problem. Well, let's see. That might be a good one to try. All right. So particle moves along that curve. So that's a relationship between its y-coordinate and its x-coordinate. You with me? That's kind of like the correct way to look at an equation that you need to have in your head. So this is y. Oh yeah, Jeff. Let me see. Why is it not working? Y equals 2 sine pi x over 2. I think is what it says, yes. As the particle passes, so this is the snapshot point. 1/3 1. Its x-coordinate increases at a rate of square root of 10 centimeters per second. So now you start to see how important it is to reason out if something's positive or negative, the derivative. So in this case, it's telling me it's increasing. So how do I write that in symbols, of course?